Hey y'all, and welcome back to Coding with Minmer. On today's agenda, we're going to tackle LeetCode problem 270, closest binary search tree value. After that, we'll go over an actual variant of the original question that Meta asks. As you'll see, we'll take a gigantic detour, but don't worry, it'll pay off, I promise. Let's see what we're being asked. We're given the root of a binary search tree as well as a target value. We want to return the value in this BST that is closest to our target. So, taking a look at our example here, we want to return the integer whose distance from the target of 4 is the closest. That's easy. The answer is just this 4, right? You can't get a closer distance of 4 minus a target of 4 to get 0. It's literally 0 away from our target. Let's make this a bit harder. We know that we can be given decimals in our target parameter, as seen here in LeetCode's examples. So why not something like 4.5? What is our answer now? It'd be 5, right? Its distance would be the 5 minus a target of 4.5 to get 0.5. Sadly, this is not right. We miss reading the literal only other sentence in our description where there can be multiple answers. And if there are, we have to return the smallest one. Not sure why LeetCode says print, that's misleading. Anyway, taking a closer look at our tree, we realize that a node of 4 is also a distance of 0.5 away from our target. And before you say something, yes, my eyesight is mediocre, but this is indeed a negative number. That said, we don't really care. All we care about is the distance from our target, whether that's positive or negative. Direction doesn't matter to us, so as you'll see, we'll just take the absolute value to normalize our distances. Anyway, since 4 and 5 are the same distance away, we're instructed to return the smaller value. Therefore, 4 is our answer. This is what we return. Okay, that's the premise of the problem. But how do we solve this in a programmatic way? We're kind of stumped, no pun intended. I'll tell you right now though, the root of all the trickiness comes down to how the input data structure is given to us. It's not just an ordinary binary tree, it's a scary binary search tree. I have no doubt it'd put us in a chokehold and overwhelm us with its many unique tree properties. What do? Are we even capable enough as engineers, especially in a growing egotistic industry? Our imposter syndrome slowly kicks in and we become very, very frightened. Why are the walls turning blood red? Okay, that part normally doesn't happen. One thing's for sure though, we're not ready. Let's dumb this problem down a bit and ask an easier variant. Maybe that way we can build some intuition. What if we were given a list instead of a tree? Okay, that's better. We're given a measly one-dimensional list. Our task remains the same. We want to return the value in the integer array that is closest to the target. Checking out our example here, this is nothing we can't solve with a for loop and an if statement. We'll loop left to right, and on each iteration, if the number is the closest number to our target so far, then we'll update a variable called result. But again, only if it has the closest distance to our target. This will manifest as another variable. Let's walk through this. On the first iteration, we have a 1. What is its distance from our target of 4.5? Well, the difference between the two is 3.5. That's definitely the closest distance we've seen so far. And we know that by comparing it with our variable that wasn't initialized yet. Our code would blow up. We don't want that. We really want this if statement to return true. So why not default it to an arbitrarily high number like int max, just so we can overwrite it with the computed distance of 3.5. Lastly, since the 1 is the closest distance to our target so far, let's update our result to the 1. Moving on to the next iteration, we have an integer of 2. What is its distance from 4.5? Well, negative 2.5, but remember we drop the sign and ignore any signage. We get a distance of 2.5. This is indeed closer than our closest distance so far because it's lower in value. So let's update both variables. The closest distance to the 2.5 and the result to the integer of 2. Okay, let's pick up the pace a bit. On the next iteration, we have a 3. It's even closer to our target than an integer of 2. That's because its distance is 1.5. So let's reflect that in our variables. On the next iteration, is 4 the closest integer to our target so far? Yes, because it's only a distance of 0.5 away. That's pretty close. Afterwards, we have an integer of 5. We carefully observe that its distance from the target is 0.5, the same exact distance as our current closest distance variable. Recall that if there is a tiebreaker, and thus multiple answers, we'll return the smallest one. In other words, we'll choose our 4 here, not the 5. This logic in concrete form will be an if statement, which should be a first-class citizen. Let's formalize it as pseudocode, where we'll update our result variable if the computed distance is lower than our closest distance. Or in the case that it ties, then we update the result variable only if the integer is lower. Okay, let's move on. From here, it's quite obvious that since a target of 4.5 is in between these two integers, that the remaining integers have a distance way too far. 6 is away by 1.5 greater than our 0.5, and 7 is 2.5 away, also greater. So we sped run those iterations, and amazing, our answer is 4. This is what we return. We accomplish this with a time complexity of big O(n). That said, our spidey senses are tingling. Can we do better? That whenever we have a data structure where everything in between a lower bound and upper bound is entirely sorted, then binary search can improve our runtime from big O(n) to log n. Let's do a quick walkthrough. Of course, to do so, we need our left and right pointers. On the first iteration, we compute the middle pointer to point to integer 4. Remember, its distance from the target is 0.5. Now, this next piece of logic is very critical. From here, do we go to the right or to the left? Let's think about it. This data structure is sorted, right? If 4 is a distance of 0.5 away from 4.5, then wouldn't any integers lower than our 4 be even further away? Indeed, that's true. The 3 is 1.5 away, the 2 is 2.5 away, and the 1 is a whopping 3.5 away from our target. Inversely, numbers to the right must be closer. For example, this 5 is 0.5 away. That's pretty close, I'd say. Let's also add this as pseudocode to our notes, that if the current integer that we're on is lower than our target, then we go to the right. Otherwise, we go left. Okay, let's finish this example. So we go to the right, we readjust our pointers as such, and the middle pointer points to A6. Are we closer? No, its distance of 1.5 is further away. That means this value of 6 is too high. Therefore, we want to go left in our binary search. To play devil's advocate, any number to the right of 6 is literally higher in value and would produce a further distance. Literally the opposite of what we're trying to go for. Anywho, going left lands us with the middle pointer pointing to 5. But recall from our linear solution, integer 5 is the same distance away from our target like integer 4 was. But remember, we bias towards the smallest value, so we keep the 4. Continuing our binary search, recall our rule. 5 is greater than our target of 4.5. We go to the left. Readjust the pointers like so. And we look at that. Not only have our pointers crossed, so our algorithm is done, but the right pointer also happens to point to the answer of 4. That's cool. But what we'll actually return is this variable right here. Our answer is 4, and this is our ultimate return. The time complexity is an impressive log n. Amazing. With this, we're feeling more confident. We feel a surge of energy. We're ready to face the binary search tree. Here's our binary search tree. It's really not that special. We can think of it as our list from moments ago, where we traverse from the lowest integer all the way to the highest one. If we can somehow do the same thing in our tree here, we'd have ourselves a solution. But how? To see the intuition, recall its unique property. For any given node, take the root node. Every node in its left subtree is lower in value. Oppositely, every node in its right subtree has a higher value. This puts the current node of 4 right down the middle between the two. This should remind you of something or trigger PTSD, one or the other. Let's look at one more example. At node 2, its left subtree has nodes lower in value, namely the 1. The current node has the next incremental number, 2. Lastly, its right subtree has nodes higher in value, the 3. What do you know? This visits nodes in order from 1, 2, 3, and extending this 4, 5, 6, 7. Okay, I'm sure by now you're yelling at your CRT TV, so I'll get to it. We're gonna use the in-order tree traversal algorithm. With this, we'll be able to visit nodes from the lowest value to the highest one as if it was one huge zigzag-looking list. Not only that, we'll reuse the same logic from our easy list variant. Let's give it a try. We start at the root node, where in-order traversal instructs us to go to the left subtree to node 2, where we'll recurse and do the same thing. At node 1, we'd like to stop and process it, but as with recursion, we can't until we hit a base case. Luckily for us, the left node doesn't exist. It's a null pointer. This is our only base case. We'll return back to the parent. Here, we'll happily process the current node, where we'll execute a familiar if statement. Is node 1's distance from our target of 4.5, which comes out to be 3.5, closer than 2 billion? Duh. Let's update the closest distance. And our result here to the 1. This should be feeling like deja vu. Afterwards, LCR next tells us to go to the right subtree, but there's also a null pointer there. We'll backtrack where now we're fully done with node 1. We'll continue where we left off at node 2. Here we process the current node. 2 from 4.5 is closer than node 1. It has a smaller distance of 2.5. Let's update that. And since we did that, update our result to the 2. Afterwards, we go to the right subtree, landing us at node 3. We go to the left, nothing there. Process the current node. What's node 3's distance from a target of 4.5? It's 1.5, surely smaller than 2.5. Let's update this variable. And our result. We go to the right, nothing there. Backtrack to node 4, and I'm realizing this is very redundant. Let's fast forward. At node 4, is distance away is only 0.5, so let's update the closest distance as well as our result like so. We then go to the right, and as at node 6, the recursion tells us to go left, left again, nothing there. Process the current node 5 has the same distance as 4, but we take the lowest one. This is our if statement action, so we'll keep the 4 and move on. To the right, so pointer, we backtrack to node 5, back to node 6, where we process node 6. Also now its distance is higher than 0.5, do nothing, go to the right. At node 7, we go to the left subtree, and base case, so we return. Process the current node, its distance from a target of 4.5 is higher than 0.5, so we don't update our result, go to the right. And great, 4 is closest to our target. This is what we return. Our time complexity is big O(n) because we visit each node one time and one time only. The space complexity is also big O(n) because of the recursive frames in our DFS implementation. This algorithm works, but we can do better. Turns out we can improve the time complexity to log n in the best case. Remember, in a data structure, if we have a lower bound and an upper bound, in which everything in between is completely sorted, then binary search is an applicable and flexible algorithm. I'm going to take this one step further and say that we can reuse our binary search algorithm as it pertains to a list or a BST data structure. The two aren't as different as we think. Let's look at them side by side. For one, observe that an in-order traversal of our BST here produces an array of sorted integers. And thus, a binary search will operate in an eerily similar fashion in both data structures. We'll bounce from data structure to data structure to help guide us through the optimal solution. So, recall on the first iteration with our list, our middle pointer first pointed to a value of 4. It's no coincidence that this is also the value of our root node. Let's pull out our pseudocode notes and realize that node 4's distance from a target of 4.5, which is 0.5, is the closest one yet. Let's update our two variables. Next up, in our list, did our binary search make us go to the left of 1, 2, 3, or to the right of 5, 6, 7? It was the right. So adjusting our pointers like so lands us at an integer of 6. This influences our decision in our BST. Do we go to the left subtree of the 1, 2, 3 or the right subtree of the 5, 6, 7? To make sure we know what we're doing, let's pull up our second note in our pseudocode where we go to the right if the value is lower than our target. Indeed, it's true, 4 is lower than 4.5. Let's go to the right, landing us at node 6 also. Here, a distance of 1.5 is not closer than our distance of 0.5. So we don't overwrite any variables and we move on. Next up in our list, again, 6 is greater than our target of 4.5, so we went to the left. Doing so places us at an integer of 5. Likewise, in our BST, we'll reassign the root to its left child, where we'll apply the same if statement. Is the distance of 5 from our target closer than our closest target so far? Not exactly, it's equal in distance. In this case, we take the smaller value, so we keep the 4. Now, on the last iteration in our list, we go to the left because 5 is higher than our value here. Doing so makes the 2 pointers cross and we're done. And our tree will simulate this exactly and go to the left. But wait, we're at a null pointer, but that's a good thing. That tells us we need to terminate our algorithm. But on that note, there's not a loop to terminate in the first place. In retrospect, we can run a while loop so long as our root pointer is not null pointer, and on each iteration, we can move the root down 1 level to the right or to the left. Amazing, this is our answer. This is what we return. As for the time complexity, it's log n, because in this case, we have a perfectly balanced tree. Do you notice how we roughly discard half the nodes on each iteration? And when we went left here, we discarded roughly half. That said, I know what you're thinking. If we're given a linked list as a binary search tree, then in the worst case, our time complexity is big OH, where h is the height of our tree. The space complexity is big O1 because we only used fixed variables, nothing else. And look, I know this was a longer explanation to explain a technically easy LeetCode problem, but there's a lot to be learned from BSTs, their properties, and patterns that we can infer, especially in relation to other data structures. All right, it's time to look at the code. Let's initialize the 2 variables we need, the closest distance, which we initialize to a default of 2 billion, as well as our result variable. Let's return it before I forget. Now for our binary search, we'll run a while loop so long as our root reference is not null pointer. On each node, we'll compute its distance by taking the delta between the root and the target parameter. Remember though, we need to take the absolute value because we don't care about the signage. Now we'll introduce our very important if statement. Is this computed distance lower than our closest distance so far? Or, in the case that they're both equal, is the current node lower than our result so far? If either case is true, we'll update both variables and result to the current value. After this, we have one more piece of very important logic. We'll have to choose to go to the left or right in our binary search. That if the value of our root is lower than the target, then we'll go to the right. Otherwise, we'll go to the left. Now, I'm not sure how good your memory is, but I did subtly go over an optimization in the first minute of the video. So if the distance that we compute is ever 0, we'll shortcut and return the current value. And that wraps it up. Let's look at the variant. It's goffable, nothing less of a nuisance. The variant is tricky and not tricky at the same time. It's a variant that doesn't know what it wants to be. The only difference here is that we're given our target parameter as an integer. It's no help to us that LeetCode never specified the type in their description. It's only really displayed in their examples. I've seen a lot of candidates mess this problem up because they assume they're given a decimal. But make sure you clarify this with your interviewer. But with that said, this barely changes anything in our code. Let's take a peek. First things first, our function signature changes, where the target is now given to us as an integer. The only implication this has is anything that pertains to our math. In other words, the type of our closest distance should now be an int. Same goes for our distance variable here. Those are all the necessary changes. Thanks for tuning in, and good luck on your interviews.